In this video, we will look at two intersecting planes. When two planes are parallel, they don't intersect, but if the planes do intersect, then they intersect in a line. And if you want to check that the planes are parallel, look at their normals. If the normals are scalar multiples of each other, as they are in this example, then the planes are parallel. And it doesn't matter if they point in different directions, because -2 is also a scalar. Now we're going to discuss here the thinking process that leads to this equation for a vector in the line of intersection. So we have two planes intersecting in a line, and this is an equation for a vector that lies along that line. So we start off with the typical idea that we have for a normal. A normal is a cross product of two vectors in a plane. And that, of course, means that the normal is orthogonal to v, which is one of the vectors in the plane, and it's also orthogonal to the other vector in the plane. In fact, it's orthogonal to all vectors in the plane. Now let's look at the situation for a vector along the intersection. Now, if a vector is lying in the intersection of a plane, then it lies in both planes. Therefore, it is orthogonal to the normal of the first plane, because it lies in the first plane. It's also orthogonal to the normal of the second plane because it lies in the second plane. Now these equations are lined up for a reason, so that you can see how to make a substitution in terms. So the normal is perpendicular to v, and the normal is perpendicular to u. Well, VL is following the same rule. It's perpendicular to two vectors. They just happen to be n1 and n2. So we're going to replace the n here by the vector in the line. Then these other vectors are being replaced by n1 and n2. And that's what's being shown here. So with those replacements, then this equation on the top becomes this is VL equals N1, the cross products of N1 and N2. We're very used to thinking of the normal being the cross product of two vectors in the plane, and now we're thinking of both normals, the cross product of them, lying in the intersection. And just a little bit of thinking in a different way. We're very used to thinking the other way, but this works too. Those two normals give a vector perpendicular to them that lies in the plane of their intersection. And that is the vector in the intersection. We want the line there, but we're going to use this vector to create the parametric equation for that line. So here's an example of creating that vector in the line. We have the general equation for a plane. And we remember that the ABCs are the components of the normal. So with that in mind, we can read off the normals for both of the planes. In this case, N1, and I'll write it in with the pointy brackets, 3 minus 6 minus 2. And N2, it's a vector with components 2, 1, and minus 2. So now we take their cross product and end up with a vector, and this is the vector along that line. To take the determinant here, I'll just write out cofactors. We have I times the cofactor matrix, and it's minus j times the cofactor matrix, 2 by 2 here, and then we have k and the other 2 by 2 cofactor matrix, and we take those determinants and we get this expression. So there's the vector in the line for these two planes, two intersecting planes. Now we need the parametric equation for that line, and the parametric equations include an R naught and a V. Well, we have a V. We have a vector in the line right here, so we can use that. We already have that. We know what it is. But now we have to construct R naught. Let us recall what this equation represents. To write this equation, we started with 2 points. Of course, I have to draw them in a plane here since I'm not very good at drawing in 3D. So here's point 1 and here's point 2. And then we created position vectors to those points. And so we need a coordinate system here. And here was our R naught, and here also from the origin was our R1. So the only reason we used R1 was to create this vector. Well, that's not a very good vector here. This vector that we placed between those 2 points. And we placed it there because we treated it as a general vector. If we had written it as a position vector, it would be somewhere down here and it wouldn't have as much meaning. So we put it there between the, and we called that B. But it doesn't matter how we get the vector that represents that direction. So instead of that B, we're using BL. That was the cross product of the 2 normals. Now for R naught, the way we constructed that is having some point along the line. At this point we have VL, but we don't have a point along the line, and we're going to have to find that from the equations for the planes. That's all we have available. So we have the 2 equations for the plane that we had before. Here's one of them, and here's the other equation for the plane. Now, for the point to be along the line of intersection, it has to belong to both planes, just as that vector belonged to both planes. So that means that the x, y, z's of the line, the point, has to satisfy this equation, and it also has to satisfy that equation. Okay, we are looking for 3 values to make up that point, but we only have 2 equations. So here's how this is done. We choose one value. Choose one for z, or choose an x, or choose a y. Then we're left with 2 equations and 2 unknowns here, which we can solve. We solve that, we get x equals 3, y equals -1. Since we'd already selected y of 0, there's the point in the plane. Now it doesn't matter what point you pick, because the parameterization will look a little bit different. As long as it lies in both planes, then it lies along that line. So the parameterization is different, meaning that it looks different, but as t varies from -infinity to +infinity, every point on the line is traced out. So now let's put everything together and write the equation, vector equation for the line that lies in the intersection between these 2 planes. So we started off with an equation for plane 1, equation for plane 2. From that we could read off the normals for both, take their cross product, and get a vector, this VL, that lies in the line. For the 1 point in the line, we went back to these equations, we picked a value for z, found values for x and y, and end up with a point in the line. Our R naught is 3, -1, and 0, and from that, of course the 0 is here, we construct the equation, the vector, the parametric equation for the line in the intersection of these 2 planes.